In Chapter 16, Section 5, we'll look at the curl and divergence of a vector field. So let's find out what they're about. In the first problem, it says, show that the vector field F can't be written as the curl of another vector field, that is, F does not equal the curl of G. So for there to be a vector field that can be written as the curl of G, we would have to get the curl to be equal to 0. But first we're going to find the divergence of F. So the divergence of F is equal to the gradient vector dotted with the vector field. So what this is going to look like is it's going to look like the partial derivative with respect to x of whatever is the p. So let's actually write this first. F can be written as p in the I direction plus q in the j direction plus r in the k direction. And so the divergence then would be the partial derivative with respect to x of p plus the partial derivative with respect to x of y, of q, plus the partial derivative with respect to z of r. And so we're going to do this with this where we have the divergence of F would be partial with respect to x of this first term, x, what is it, z squared. And then it's going to be plus partial with respect to y of the second term, x seventh, y to the first, z to the third, then plus partial with respect to z of the third term, negative y cubed. And this should be a scalar because we're dotting a gradient with, we're dotting two vectors basically. So we should get a scalar out. And it should be 0 if we want to be able to find some vector field G for which we can curl that and get a different vector out. So if we take the partial with respect to x, this would be z squared, plus the partial with respect to y of the second term would be x seventh, z to the third, so the y term will completely go away, and the partial derivative of y with respect to z is 0. So the divergence of f is z squared plus x7 z3, which I have typed right here, and it's not 0. So the idea here is we needed, and you can click these little theorem buttons that'll show you the actual written out kind of longhand equation. But basically, if the divergence of f is not equal to 0, then we can't get the divergence of f to equal the divergence of the curl of G. So that's going to contradict this. Now, this is kind of confusing, but we're going to see some examples later where we're going to find this special vector and this special vector field by taking curls of G, and we'll get them equal to 0, and then we'll say they're conservative, and then we can take integrals of the partial derivative equations to find a general form of an equation, a vector. It's very actually similar to what we did in 16.4 towards the end of that section. Okay, so that's problem 1. Problem 2 says the vector field F in the xy plane looks the same in all other horizontal planes. In other words, F is independent of Z and its Z component is 0. So describe the divergence of F. Well, again, the divergence of F would be equal to the partial derivative of the vector field with respect to x of p plus partial with respect to y of q plus partial with respect to z of r. But notice that this is only in 2 dimensions, so this part will completely go away. There is no third dimension in this case. z component is 0. And if we look at this equation, these vector fields are all, no matter what x is, these are just, the y value is growing. And if we look at these lines, they're getting shorter as y is getting bigger. So the only way that these can be shrinking like this is if this q component has some negative y in it. So these are getting smaller. So the divergence would have to be negative for that to happen. Okay, in what direction does the curl F point? So the curl, here's an example. So, for example, let's say we had a circle and we had this vector field going like this. Well, it follows the right-hand rule, so we're going to point towards those arrows and curl our right hand, and that's going to point in the direction of the curl. So this curl, so if this is vector field F, the curl of F, and this is going to be really hard to draw, is going to point out of the page. So this is the curl of F. But with this particular picture, in 2 dimensions, these arrows just going up and they don't change at all along the x-axis of the exact same field throughout. We're not going to be able to curl our fingers in such a way to give us any result at all. So the answer here would be none of the above. Okay, and that's problem 2. Okay, so how do we calculate the curl? So when we're doing things like right-hand rule, that is indicative of a cross product. So the curl is the curl of F is equal to the gradient vector crossed with the vector field F. So we're not going to actually do it this way, but if we did want to, it would look like this. So we have I, J, K, and we would take partial with respect to x and p, partial with respect to y and q, partial with respect to z and r. And you can do this based on cross product rules we learned a while back. You would get the following, so we're just going to use this result. It would be partial r with respect to y minus partial q with respect to z in the I direction, plus, so basically you cover up the I column and then you do a 2 by 2 determinant of the bottom 4 values, so it'd be d, dr, dy, dq, dz with a subtraction there. Similarly, for the j component, you would, and actually you need a minus there. Okay, so we're going to absorb the minus in this, so here's how it's going to look. It's going to be dp with respect to z minus dr with respect to x. And so for a cross product, it's plus minus plus, so the only way that this second term would be plus is if they switch the order on these two partial derivatives, which they did. So it normally would have been dr dx minus dp dz, but we want to make this plus out here, so we just swap those two. That's in front of the j, plus cover up your third column, 2 by 2 determinant should be dq dx minus dp dy in front of the k. Let me just make sure I've got that right. Yes, that's correct. So this is the equation that we can just use for the curl of f, where again f is equal to some p in the I plus some q in the j plus some r in the k. Okay, so let's see what we have for this particular one. So the vector field is 7y squared z3, that's p, 14xyz cubed, that's q, 21xy squared z squared, that's r. So the curl of f would be equal to dr dy. So the derivative of r with respect, the partial derivative of r with respect to y would be 42xy z squared. So we just bring that 2 down on the y in front and then subtract 1 from it. That's the first term. Minus dq dz. Derivative of q with respect to z. The 3 times the 14 would give us 42, and then it's going to be xyz squared. And that's in front of the I component, plus dp dz. The derivative of p with respect to z would be 21 y squared z squared minus dr dx. Partial derivative of r with respect to x would be 40. No, with respect to x, the x would just go away. It would be 21 y squared z squared. In the j, plus dq dx would be 14yz cubed, so the x would just go away. 14yz cubed minus dp dy would be 14 y squared would become y, and then z3 on the k. And if you look, these terms all are exactly opposite and equal, so we're going to get the curl of f is 0 in the I, plus 0 in the j, plus 0 in the k. And if we get that, we say that this is a conservative vector field. So we're going to say f is conservative. And only if f is conservative, now we'll remember from the last section, section 16.4, we can say that the partial derivative of some vector f has to equal the first term, 7y squared z cubed, which implies that the function xyz would be the integral of that fx with respect to x. So if I integrated that with respect to x, I would just pick up an x, 7x y squared z3. Fy would equal the second term, 14xy z cubed, which implies the function of x with respect to xyz would be equal to the antiderivative of this with respect to y would be 14xy squared over 2 z cubed, and that's going to equal, this 1/2 can come out front, 7xy squared z3. Then the last one, the partial derivative with respect to z, has to equal the third term, the r term, 21xy squared z squared. That implies that if I take an integral with respect to just z now, it's going to be 21xy squared z cubed over 3. So the antiderivative of z squared is z cubed over 3. Bring the 1/3 out, we're going to get 7xy squared z cubed. And so we basically have all three equations are the same, so that is the equation. So that is the function that we're missing. Now technically each of these could have had, so if I did the first one with respect to x, there could have been a function h that had y's and z's in it only. That would have gone away in the partial derivative with respect to x. And there could have been a function h on this one that only had x and z on it, because it was with respect to y. And this one could have had a function that had just x and y on it, because we only considered the antiderivative with respect to z. So if any of these functions, any of these three functions could have existed, because by taking partial derivatives they would have gone to 0. But I know they don't exist because we get exactly the same, let me use a different color. We get exactly the same function out of those integrals. So if I had the same function then a different function, I could have assigned that to one of these h's and said, okay, there's more here than what we're seeing, but since all three of these blue equations were the same, we can assume that these h equations were just 0, or some constant that goes away completely. And the simplest constant to pick is 0. Okay, so that's problem 3. Now this is kind of the approach we're going to use going forward for a lot of these. So we're just going to do this a bunch of times and see how it plays out. Okay, problem 4 is really similar, so I'm going to keep this up here. And we're going to call this term P, and this term Q, and this term R. So we have the derivative, the partial r, partial y, so it would be 12 x squared y z squared minus partial q, partial z. Partial q, partial z would be 12 x squared y z squared. So we took a derivative of z cubed, 3 came down, made that 4 a 12. The 3 becomes a 2. Then we have dp dz. dp dz would be 12 x, see I did z, x y squared z. dr dx would be 12x y squared z squared. I missed a squared here. Okay, then the last two, dq dx, would be 8x yz3 minus dp dy would be 12 x y z squared. And I think I also have an error here. This should have been yz squared, not z3. Okay, now if you look at this very carefully, this first term is 0 in the I. The second term is 0 in the j. The third term, however, is minus 4xyz squared in the k. So those two terms don't cancel each other perfectly. And because of this, we would say f is not conservative. So we have to have the curl be equal to 0. It's conservative. We have to have the curl equal 0 in all three components, the I, j, and the k, for it to be conservative. And if it's not conservative, then we're going to say there is no function f, x, y, z that we're going to be able to find using integrals of those partial derivatives. So we're just going to say this function will not exist, does not exist. Okay, but the approach, very similar, but we didn't get the 3 zeros, so we can't then find this function, little f of x, y, z. Okay, problem 5, very similar. We have e to the yz is going to be our p, xz e to the yz is going to be q, xy e to the yz is r. And so if we take the derivative of r with respect to y, we're going to get x e to the yz. Now this is, you have to be careful on this one, this is product rule. So we have a y in front of the e and a y attached to the e as a power. So in the first part, we just take a derivative of y, which is 1, and get x times 1 times e to the yz. Then we get plus, leave the first term alone, xy. Then the derivative of e to the yz would be z, because that's a constant now in front of the y, e to the yz. Okay, so that one's a little interesting. You've got product rule there to account for. Okay, so two terms for that dr dy. Minus dq dz. dq dz is very similar. It's going to be x e to the yz plus xyz e to the yz. So again, product rule in that one also, you've got a z in front of the e and a z attached to the e as a power. So the first z becomes a 1, and then you get x and e to the yz, and then you do another round where you leave the z alone, take a derivative of e to the yz, but y would be a constant in that in front of the z, which is the variable, so the y would come down front. Okay, now for the second set of terms, we have dp dz. Well, that one's not so bad. You would have a y e to the yz. So in that one, y is a constant, z is a variable. dr dx would be, okay, there's only one x, it's in front of everything, so it just goes away, and it's going to be y e to the yz. And the last two terms, dq dx, would be, again, the x just goes away, so it's z e to the yz. And dp dy, you would bring the z down, e to the yz. And if you look very, very carefully, these two terms are exactly the same as these two terms, but this is a minus in front of it, so both of them are negative. This is exactly the same as that. This is exactly the same as that. They're all the same, but they differ by a minus sign, so they are all going to be zeros. So we get the curl to be all zeros, so we would say f is conservative, and therefore we can find a function x, y, z that should represent this function if we start taking partial derivatives of it. So we would say the partial with respect to x should be equal to the first term, e to the yz, which implies that the function would just be x e to the yz. Then we would have fy should equal the second term, xz to the, times e to the yz, which implies that this function, we take an antiderivative of this term with respect to y, we would look at this and say, okay, if y is my variable, then when I take a derivative of this, the z will come down. So to undo that, we get rid of that z and say, this should have been x e to the yz. So again, if you look at that and you take a derivative of that function with respect to z, you treat x as a constant, y as a constant, but the, z as a constant, because we're doing it with respect to y. So you would bring the y, bring the z down front, and that's how you would get back to what fy is. Okay, last one, fz should be equal to the last term, xy e to the yz, which implies, same argument, if I'm doing this with respect to z, y is a constant, x is a constant, so this y in front of the e, we can bring it back up into the power because we're going the opposite way. So this could have just been x e to the yz. And again, if you take partial derivative of that with respect to z, you will get x, y, e to the yz. And because those are all the same, I don't have to introduce any other potential functions. So we can say there are no other constants of integration or anything like that. So we would say the function is this, x e to the yz. So all the same, all same. So that is the answer. And again, the whole point of that is I take a partial with respect to f and I get the p, take a partial with respect to y and I get q, take a partial with respect to r and I get, with respect to z and I get r. So I can recreate that vector field just by taking partial derivatives, which is the same as taking a gradient. So we're basically taking a gradient of this and we're getting back to where we started. In problem 6, they want us to look at things a little differently. They say, is there a vector field G in 3 dimensions, R3, such that curl of G equals this vector, yes or no? So to find that, we're going to take the divergence of the curl of G. And if that equals 0, then we can say, yes, there is a G such that the curl would equal that vector they gave us. So the divergence of curl G would be equal to, let's see here, so we're going to say the divergence of curl G, that's going to equal, in this problem, partial with respect to x of the first term of the curl, x sine y, plus partial with respect to y of the second term of the curl, cosine y, plus partial with respect to z of the third term in the curl of G, z minus 7xy. This is going to be partial with respect to x, the x just goes away, so you're going to get sine y, plus partial with respect to y of cosine y is negative sine y, plus partial with respect to z is 1 minus 0. And we're going to get, this is equal to sine y minus sine y, so this whole thing is 0, but then we have plus 1 and minus 0, so this whole thing is plus 1. If it was 0, we could work with it, but we can't because it's equal to 1. So is there a vector G such that the curl is this? No. There is no such G because the divergence of the curl G is not equal to 0. So we need that to be equal to 0 to have such a curl, to have G to be able to have a curl like that. Okay, problem 7 is pretty much the exact same problem. It says calculate the divergence of the curl. So we have partial with respect to x of the first term, xyz, plus partial with respect to y of the second term, negative y to the 9th, z to the 8th, plus partial with respect to z of the third term, y8, z8, y8, z9. So we're going to get, this is yz, this is minus 9, y to the 8th, z to the 8th. This would be plus 9, y to the 8th, z to the 8th. Just using partials here. So in the second term, only y is your variable, so bring the 9 down, subtract 1 from the power of y. In the third term, bring the 9 from the z down, subtract 1 from the power 9 on z. Now these two are exactly the same, opposite and equal, so they'll be 0. But we're still stuck with this yz, which is not equal to 0. So because of that, it's the same thing. No, this can't be a vector field G, and because there's the divergence of the curl was not equal to 0. Okay, problem 8 is a kind of like a theorem problem where they're going to give us some things and we have to decide what we can do. So it says F is a scalar field, F and G, capital F and capital G are vector fields. Then we can have scalar field times vector field F dotted with vector field G, and vector field F crossed with vector field G. So these are things that can be done. So it says find an identical expression assuming that the appropriate partial derivatives exist and are continuous. The divergence of F plus G. Well, if we know that F and G are two vector fields, and they can be broken down like this, we can dot them together, then we can say the divergence of F plus G can also be split up into the divergence of F plus the divergence of G. So, and we could prove this if we wanted to with pick two continuous partial derivative vector fields, and we could show that this is true, but for the sake of time, let me just say that you can do this. So that would be the answer for this one. Okay, problem 9 is pretty similar also. So we have the divergence of scalar field F times vector field F, and we can, in one case, pull that F out and make it F times, let me not write times so we don't confuse it with the dot product, F times the divergence of the vector field F, but then we also get the divergence of F, the scalar, times the vector field F, but the divergence of F is the gradient of F. So rearranging ever so slightly, we get scalar field F times the divergence of vector field F plus, let me write it the same way they have it, F dotted with the gradient of F. So those are equivalent. That'd be problem 9. Okay, last problem. We have a vector R is just x, I, y, j, z, k, and R, so no bold, it's not bolded, is the magnitude of R. So let's kind of write this a little bigger. xi plus yj plus zk. Now, R, unbolded, is going to equal the magnitude of R, which would be the square root of the sum of these things squared. So it's x squared plus y squared plus z squared. And we're going to kind of hold on to that. Okay, so this says find the gradient of R. Well, that is going to be so we're working with this square root up here. It's going to be equal to the partial with respect to x of, and I'm going to write this a little differently, x squared plus y squared plus z squared raised to the 1/2 in the I direction, plus we're going to have the partial with respect to y of the exact same thing. X squared plus y squared plus z squared raised to the 1/2 in the j direction, plus partial with respect to z of x squared plus y squared plus z squared to the 1/2 in the k direction. Well, if I take a partial derivative of this, it's going to be 1/2, leave the bubble alone, raised to the minus 1/2 times the derivative of the inside, when I'm considering x as a variable, derivative of x squared is 2x, and the other two terms go away. And that's in the I direction. Now, by symmetry, the other two derivatives are exactly the same. The only thing that changes are the two terms, the terms on the outside. So it's going to be 2y now in the j direction. Oops, this should be minus 1/2 also. And then the third term, x squared plus y squared plus z squared raised to the minus 1/2 times 2z. And that's in the k direction. But if you notice, what we're going to get is this 1/2 cancels with this 2, this 1/2 cancels with this 2, this 1/2 cancels with this 2, and on top we just get x, y, and z, so we get x in the I, y in the j, z in the k, and they all have the same denominator, the common denominator of this raised to the negative 1/2, which is just this, x squared plus y squared plus z squared. But if you look at this, this on top is the original r vector, and this on bottom is the magnitude of r. So let me actually write that like that. That's the magnitude of r. So the gradient of r is just the original vector divided by its magnitude for this one. Okay, now we do the curl of r. And let me write what the curl was. So it is, write it again, dr dy minus dq dz in the I plus dp dz minus dr dx in the j plus dq dx minus dp dy in the k. And in this one, p is x, q is y, r is z. So we're going to have dr dy. Well, r is z, so the derivative of z with respect to y is 0. dq dz. Q is y, so the derivative of y with respect to z is 0. Plus dp dz. P is x, derivative of x with respect to z, 0. dr dx, derivative of r, which is z, with respect to x is 0 in the j. Plus dq dx. Q is y, so the derivative of y with respect to x is 0. dp dy. P is x, derivative of x with respect to y, 0. So this is 0, 0, 0. It is a vector 0, so they wrote it as bold. So it's like bold 0. Okay, so that one's not too bad. Now, the gradient of 1 over r. So if r is the square root of x squared plus y squared plus z squared, the gradient of 1 over r would be the gradient of x squared plus y squared plus z squared raised to the minus 1/2. See if I got my parentheses like that. Which would be the partial derivative of this with respect to x. It's going to look really similar to what we just saw. Minus 1/2 x squared plus y squared plus z squared raised to the minus 3/2 now, because that minus 1/2 subtract 1 gets bigger in the negative, times 2x in the I direction. And then it's going to be plus negative 1/2, same thing, x squared plus y squared plus z squared to the negative 3/2 times 2y in the j direction. And then it's going to be plus minus 1/2 x squared plus y squared plus z squared to the negative 3/2 times 2z in the k direction. And again, the 2's are going to cancel, and what you're going to get on top is minus x in the I, minus y in the j, minus z in the k. So these minuses do stick around, but all the 2's cancel. And on the bottom, we actually have, this is r, this is the square root of x squared plus y squared plus z squared to the 3rd power. So on top, that is the same as minus r vector, and on the bottom, this is the same as magnitude of r to the 3rd power, cubed. And so we have negative r vector divided by its magnitude cubed. Okay, now for the natural log, see if I have enough room. So now we're doing the gradient of the natural log of r. And it's the scalar r, not the vector. just like these other ones were. So it's going to be the gradient of the natural log of x squared plus y squared plus z squared raised to the 1/2 power. That's what r is. Now we're going to use a property of logarithms that says you can bring this 1/2 down in front. So this is equal to the gradient of 1/2 the natural log of x squared plus y squared plus z squared. But again, we're going to take partial derivatives of that with respect to x, y, and z. So what we're going to get is 1/2 is going to carry along. The derivative of natural log of that is 1 over all that stuff times the derivative inside, which would be in terms of x, 2x. Then we're going to get 1/2 again, 1 over all that stuff, x squared plus y squared plus z squared, times 2y. Then the last term is going to be 1/2, 1 over x squared plus y squared plus z squared, times 2z. And once again, 2 cancels 2, cancels 2, cancels 2, cancels 2, cancels 2. And we are left with they have a common denominator on top. Oh, I forgot to write the vectors in here. So this is I, this is in front of J, and this one's in front of K. So we're going to get xi plus yj plus zk all over the common denominator of x squared plus y squared plus z squared. Well, this on top is just r, and this looks exactly like the magnitude of r without the square root. So the magnitude of r without the square root is just the magnitude squared. So we get vector r over its magnitude squared. And we did that just by taking these partial derivatives of the various forms here and accounting for everything and simplifying. So that will complete Chapter 16, Section 5, Curl and Divergence.